We are from Group 4 and today we are going to present about Experiment 7, Torricelli Theorem. This is our group members. The introduction. In 1643, Evangelista Torricelli, a scientist, has developed Torricelli's theorem and it can be linked between the liquid velocity and the height h. Assume that a hole in a liquid container filled with water is located h below the cylindrical container's top surface. Water eventually begins to pour from that hole of the container with velocity and reaches the ground. Torricelli's theorem is applied here, and the process by which the water exits the container through a hole is known as influx. This is the reference number. The objectives of this experiment is to measure the velocity of the water exiting the container at various heights, and also to verify Torricelli's theorem by comparing experimental data with the theoretical value and value of velocity. The scope of this experiment is we test with 5 different volumes of water with 1.5 liter, 1.25 liter, 1 liter, 0.75 liter, and lastly 0.5 liter. After that, we repeat 3 different heights from ground mark S0 to the orifice, which will y equals to 32.5 cm, 52 cm, and lastly 72 cm.
Next is the theory or working principle of Torricelli's law. The theorem is derived from the Brownian equation and can be stated as V is equal to square root of 2gh, where V is the speed of the fluid exiting the orifice, g is the gravity acceleration, and h is the height of the fluid above the orifice. Torricelli's theorem is based on the conservation of mechanical energy and in a fluid, and from the Bernoulli's principle expressed is represented by 3 types of energy, which is potential energy, kinetic energy, and pressure. For any circumstance, Torricelli's equation is derived. Viscosity and other losses must be ignored, and the orifice must be tiny. In Bernoulli's equation, if a fluid is flowing through a very small orifice, the velocity of the fluid at the large end can be ignored. We can take a bottom of a big tank as an example for this situation. According to Bernoulli's principle, this equation refers to how pressure and velocity are inversely related in a moving fluid. In a simplified explanation, imagine a fluid is moving through a pipe with some different diameters. When the pipe narrows, the fluid has to flow faster to maintain the same flow rate. However, since the total energy in the fluid must remain constant along the streamline, kinetic energy must increase. This resulted in a drop in pressure in the narrow section, and the result is vice versa when the pipe's diameter is widened. Some examples that are related to Bernoulli's principle is water flows in pipes, water flow over dams and spillways, and lastly is flow over riverbank and narrow channel. A quick explanation for an example of water flow in pipes, which we call as Venturi effect. In a pipe with narrow section, which is Venturi tube, water speed increase in the narrow region, causing a drop in pressure. This pressure difference is used in Venturi meters to measure the flow rate of water and other fluids by observing the change in pressure.
Experimental setup. The experiment setup will consist of a clay maker, cylindrical cylinder, measuring tape, and the setup will be as shown on the slide. Next will be methodology. A 2-meter long metal tray was positioned on the floor, extending from the base of the 3-tier metal rack to the laboratory drainage duct. The vector platform was placed on the lowest rack level, which is 32.5 centimeter height, and aligned so that its front edge matched the 0 mark on the measuring tape. A cylinder with a drill orifice was then secured to the platform using a retort stand and clamp. Thirdly, the orifice was temporarily sealed to prevent water leakage, and 1.5 liter of water was added to the cylinder. The initial water level H was then recorded. After unblocking the orifice, the initial contact point of the water stream on the tray surface was marked with clay. The horizontal X from the orifice along the plank was then measured. The time taken for the cylinder to drain T was recorded using a stopwatch. Step 3 and 4 were repeated twice to obtain average values for H, X, and T, while step 3 to step 5 were repeated also with water volumes of 1.5 liter, 1.25 liter, 1.0 liter, 0.75 liter, and also 0.5 liter. And lastly, step 2 through step 7 were repeated with the platform position on the two higher rack levels at Y52 cm and also 72 cm, which is we're going to do another experiment for the second and third experiment.
Hello doctor. So for my part, I'm going to start with the table. So this is the table for the first height from the floor to the orifice, and then the second table and the third table. So for the safety procedure, there's 5. So first is to wear safety equipment, to make sure we wear clothes, gloves, and protective eyewear because we're working with the large volumes. Second is to secure the equipment. So ensure the container holding the water is stable and properly secured to prevent it from tipping over. Third is to clear the workspace. So we have to clear any electrical equipments or any other items around the area experiment to avoid slipping hazards and keep the area dry by mopping it. So fourth is avoid direct contact with water outlet. So while the water flow with the high pressure can cause unexpected splashes, so that's why last but not least is to dispose our water properly. So there need to be a drainage system to avoid the flooding the workspace. So for the results, so these are the results we get while doing the experiment. So this is for the 52.0 cm from floor to the orifice, and this is the third result. So for discussion,
As for the discussion, number 1, in this experiment, the constant variable is the type of fluid with tap water used consistently to maintain uniform properties such as density, incompressibility, and viscosity. This ensures the applicability of Bernoulli's and Torricelli's equation in calculations. And the independent variables are the initial water level in the cylinder H and the efflux fluid vertical displacement y, defined as the vertical distance from the orifice center to the ground, while the dependent variables are the efflux fluid horizontal displacement x and the time taken to drain the cylinder T. In this experiment, the independent variable is the fluid height above the orifice H that I said before, as it is manipulated or changes naturally, influencing the outcome, while the dependent variable is the effects of velocity v determined by h. As above, constant variable include the type of fluid, gravitational acceleration g, and also the orifice size, which are kept unchanged to ensure accurate results and isolate the relationship between h and v, which we can refer to our Torricelli equation.
So for discussion 2, we have to relate the Bernoulli equation with Torricelli law for this experiment by explaining the derivation. So Bernoulli equation and Torricelli's law are closely related in fluid mechanics. Bernoulli equation states that the increase in speed of a fluid occurs simultaneously with a decrease in pressure or decrease in its potential energy. We can use the Bernoulli equation to get the equation we want, which is the velocity equals to the square root of 2 times gravity times the height. So in the Bernoulli equation, we assume that the pressure 1 equals to pressure 2 equals to atmospheric pressure, and the velocity 1 equals to 0 as velocity 0 at fluid surface, and velocity 2 equals to v, and the first height z1 is equal to h, which is the height of fluid, and also the height 2, which is z2 equals to 0 at the ground mark. So by substituting all of this into the Bernoulli equation, we can get the equation density times gravity times height equals to half of density times the velocity squared. So we cut out the density and we can get this equation, and lastly the equation we want, which is this.
okay, for discussion, for the part 3 discussion, where I have to talk about the percentage of error. So since I already stated all the percentage error we get in the experiment in the table. So in the left hand side, doctor can see how we get the percentage error using the formulas. So this is how we get the percentage error by using the formula. And then for the discussion, for the fourth discussion, where I have to talk about the source of errors and the methods to minimize the errors. So the first part, for the source of the errors, there can be 5 causes the errors. So first is the perilous error in measurement. So since the observer eye is not aligned with the level of the measuring instrument. Second is the viscous effect and turbulence. So the Troucelli's theorem assumes that an ideal situation, but in a real situation, it's not ideal. Therefore, there can be a viscous effect and turbulence in the water. Third is the air resistance. Since the water exits the hole, the air resistance can alter the trajectory and velocity of the water jet. Fourth is the hole size and the shape. Since the hole size is not in a perfect shape and there's some rough areas, so which can cause the inconsistent in the measurement in the exit of the flow. So last but not least, inaccurate measurement of initial water level and the trajectory distance. So since the water splashes, it's very hard to get the exact point, and to calculate the height from the orifice to the surface, we used a measuring tape, and it may be not 90 degrees while measuring it. So to minimize this error, we can use these 4 methods. So first is reducing the parallel error. So we have to be more patient while reading the water level. So we have to make sure that our eye directly contact with the water level. Second is the smooth the hole edges. So we have to make sure the hole is smoother. Third is using a streamline nozzle, which can help the streamline the flow and reduce the viscous effect. So last but not least is to minimize the air resistant impact, since while we're doing the experiment, it's very open area. So to minimize the air resistance, we can make sure to close down all the doors and windows. Thank you, doctor. That's all from me.
And lastly is the conclusion of the experiment. To conclude, we can say that when the height from the floor to the orifice, which is the value of H, increase, the water's trajectory distance, the value of X will also increase. For example, we take the reading from the value of Y is equal to 52 cm. At the first reading, the value of H is equal to 96.9 and X is equal to 53.1, and the second reading is the value of H is 80.1 while the value of X is 46.8. From this result, we can see that the value of X is increased when the value of H is increased. As for the percentage error from the experiment, the value of Y is equal to 32.5 cm has the highest value of percentage error, which is 63.22%. This may affected by the value of H, which is the height from the floor to the orifice. And this is the references that our group used